Okay, let's unpack this. We are, and I don't think this is an exaggeration, witnessing the most profound technical shift in modern aviation since, well, since the jet engine. I'm talking about the rise of electric vertical takeoff and landing aircraft eVTOLs. And in this new world of urban air mobility, or UAM, every single component has been fundamentally reimagined. The sources we have today are excerpts from a really extraordinary engineering specification white paper. It's the technical blueprint for the battery management system, the BMS, for what's called the P13 series parallel hybrid power system. Our mission today is to do a top-down dissection of the specification. We want to look at it through the eyes of a propulsion architect and really understand the absolute non-negotiable standards you need to certify a battery for flight. We're focusing on a single, almost mind-bending design commitment, achieving a catastrophic variable probability of 1 in a billion. Now, before we jump into the BMS itself, we should probably set the stage. We're dealing with the P13 architecture. It's a series parallel hybrid. This is the system engineers chose to conquer range anxiety. It blends the high energy density of fuel from an internal combustion engine, an ICE, with the instantaneous power response you only get from an electric drive. The P13 system uses a P1 integrated starter generator, a K0 clutch, and P3 propulsion motors. The BMS is, I guess, the choreographer for this whole complicated dance.
It is, and that choreography is absolutely the key to understanding the stakes here. The BMS is no longer just a monitor. It's an integrated high-safety integrity avionics device, and it's operating in an incredibly unforgiving 800-volt high-voltage environment, managing these extreme power pulses. You mentioned the 1 in a billion commitment. That's 1 times 10 to the negative 9 per flight hour. That isn't a goal. It's a regulatory prerequisite.
A prerequisite, so you don't even get in the door without it.
Not a chance. Specifically, this design has to comply with the EAC VTOL enhanced category. To get your type certification, you have to demonstrate mathematically, through testing, through exhaustive documentation, that the chance of a failure leading to the loss of the aircraft is less than 1 in a billion flying hours.
Can you put that number into perspective for us?
Well, think about commercial jets, which we all see as the gold standard of safety. They aim for a 10 to the negative 7 probability.
So 100 times less safe.
100 times less safe. We are talking about 2 full orders of magnitude greater safety requirement for these vehicles that are flying over our cities. And that standard, it mandates a revolutionary change in engineering philosophy.
That 10 to the negative 9 target, it just immediately exposes this chasm between a car and an aircraft. So the first thing we need to do is unpack that philosophical shift. What is the fundamental difference between an electric car's battery system and an eVTOL's?
It all comes down to where you can stop. If you look at the automotive standard, it relies on what's called the fail-safe model. So if an EV's BMS detects a really extreme fault, say a short circuit or a thermal event brewing, the primary response is to isolate the battery, cut power, and safely shut down.
The car can always pull over.
It can always pull over.
Yeah.
The system prioritizes protecting the components and mitigating risk over keeping the car moving.
Which makes perfect sense on the ground. But in the sky, you can't exactly find a shoulder to pull over on.
Precisely. In aviation, especially for eVTOLs on these dense urban routes, we have to adopt the fail operational mandate. And this is captured by a pretty chilling but fundamental concept: no place to land.
No place to land.
If you are hundreds, even thousands of feet in the air, a power interruption is an immediate catastrophic event, period. So the BMS has to be architected, redundant, and programmed to ensure that even after a failure of a critical component—
Right, even when something's already gone wrong.
Exactly. Be it a sensor, a communication line, a processor, even a group of cells, the system must sustain sufficient controlled, stable power output. The goal is what we call a continued safe flight and successful landing, or CSFL. It's not just about detecting the fault, it's about absorbing it and continuing the mission until you're safely on the ground.
To really grasp the intensity here, we need to look at the operational metrics. These numbers explain why fail operational is so essential. Let's use the source materials comparison between EV and eVTOL use. Let's start with, say, the sustained thermal demands.
Yeah, that's a great place to start. Consider the C rate. That's just the rate of discharge relative to the battery's total capacity. Your typical EV, it cruises gently, maybe pulling 0.1 to 0.3 C. It's a low, manageable thermal load.
Right.
An eVTOL, however, even in sustained horizontal cruise, is running at 1 to 1.5 C.
Wow. That's a huge jump.
It's a massive, sustained increase in energy draw. This means the cells, the connectors, everything is constantly stressed, generating far more heat over long periods. The BMS thermal management can't rest. It is under continuous extreme pressure.
Yeah.
We're pushing the limits of heat dissipation, not just for a moment, but for the entire flight.
Okay, so if the sustained C rate is that high, the peak power duration must be where the real stress test happens. An EV driver might want peak power for, what, 5–10 seconds to merge onto a highway? It's transient. What about the eVTOL?
The eVTOL has to sustain its maximum possible discharge for 30 to 120 seconds.
2 full minutes.
2 full minutes. During the most critical phases, vertical takeoff, hover, or the final vertical landing approach. And this extended high-power pulse, it creates 2 fundamental engineering headaches that the BMS have to solve. First is voltage sag management.
Yeah.
When you pull that much current for that long, the internal resistance causes the voltage to drop or sag significantly. If the BMS can't accurately predict and compensate for that sag, it risks falsely triggering a low voltage safety cutout. And mid-hover, that's absolutely catastrophic.
So the BMS has to predict the sag and keep the system above a critical threshold for 2 minutes while pulling maximum power. That sounds like a simulation nightmare.
It is. And the second challenge is the thermal load from that.
Yeah.
We're not talking about average heat. We're talking about massive localized hotspots that develop incredibly quickly because of the current rushing through the internal tabs and connectors. The BMS has to manage that heat spike from a 120-second max power draw to prevent internal damage or, even worse, initiating thermal runaway.
And finally, the lifetime utilization rate. This really hammers home the difficulty of maintaining that 10 to the -9 reliability. An EV, 300, 500 cycles a year?
Something like that, yeah. For the UAM platform, we're looking at a factor of 4 increase. The P13 system is designed for high-frequency urban routes, dozens of short hops a day. It's expected to see approximately 1,600 equivalent full cycles, or EFCs, per year.
1,600.
1,600. This means the battery is aging at 4 times the rate of a normal automotive battery. This accelerated degradation changes everything about maintenance and operations. The BMS can't rely on simple lookup tables. It has to become an extremely accurate, predictive modeler of cell health. It has to ensure the aircraft is never dispatched on a mission where the battery has degraded so much that it compromises that vital 120-second power margin needed for a safe landing.
So moving from those stress factors to the actual operational requirements, the BMS for this P13 hybrid architecture, it's doing a lot more than a pure electric BMS, right?
Oh, absolutely. I mean, if we use a top-down structured approach that MECE framework aerospace specs love, we can break the BMS's job into 4 core functions. You've got high voltage safety, thermal management, precise state estimation, what we call SOX, and then uniquely for the P13, the hybrid energy coordination functions.
Let's start there, the hybrid challenge. When we talk about multimodal energy switching, what are the key scenarios this BMS has to support that a normal EV never even thinks about?
The first, and maybe the most demanding, is e-boost mode. This is the scenario where the battery has to provide its maximum pulse current, that 5 to 10 C discharge, for a prolonged period during takeoff. But here's the critical aviation application: one engine inoperative or OEI scenarios.
If the engine fails.
Exactly. If the ICE component fails, the battery must instantly compensate for that lost power. And the BMS can't just allow this maximum output. It has to constantly forecast the precise available power envelope to the VCU. This prevents the VCU from demanding more power than the battery can safely deliver, which would cause an unexpected mission-critical power cutoff.
So the BMS is the honest broker, constantly telling the VCU, this is exactly how much thrust I can give you right now and for exactly how long.
That's a perfect way to put it. The VCU flies the aircraft, but the BMS sets the power limits based on real-time cell physics. The second unique mode is in-flight charging. We call it airborne replenishment. This is the huge advantage of the hybrid. During the cruise phase, the P1 generator is running, constantly recharging the battery.
Charge sustain mode.
That's the one. It sounds simple, but generator charging is electrically dirty compared to a clean, ground-based charger.
What do you mean by dirty?
Well, the BMS has to manage the power curve, sure, to minimize heat waste. But more importantly, the generator introduces high-frequency microcycles and significant current ripple. If you've ever heard a slight hum from an electrical system, that's ripple. On a battery, this ripple is an aggressor. These high-frequency microcycles superimposed on the DC current, they significantly accelerate battery degradation. The BMS algorithms have to filter, monitor, and compensate for the impact of this electrical noise perfectly. Otherwise, that 1600 EFC annual cycle count will rapidly balloon into a much shorter, unusable lifespan.
That's a great insight. Okay, finally, let's talk about the synchronization element, the K0 synchronization. This is where the electrical and mechanical systems meet.
Right. The K0 clutch is the linkage, and for it to engage smoothly, the P1 motor speed, which is driven by the ICE and generator, has to closely match the P3 motor speed, which is driving the rotors.
If they don't match.
You get a violent torque spike, you could damage the mechanical systems, the electrical systems, or both. So the BMS's crucial role here is feeding the VCU with real-time state of power, or SOP, data. The VCU takes that SOP and uses it as a critical input to adjust the P1 motor speed before it engages the clutch. The success of that hybrid handover hinges on the accuracy and speed of the BMS's SOP report.
Which brings us right into state estimation, or SOX. This is the core intelligence of the BMS. And this is where estimation accuracy stops being about maintenance and becomes a primary safety metric. Let's hit the three critical ones, starting with the one everyone knows. SOC, state of charge, the fuel gauge.
It's the fuel gauge, but with life or death implications. The pilot relies entirely on the SOC reading to make critical decisions. For example, determining the no-go-around point, the final moment where they still have enough energy to abort the landing and climb away, or estimating the remaining landing time.
And because of that, the spec is brutal.
It is. The SOC error must be controlled to less than 1% across the entire dynamic mission profile. That 1% error margin is critical because regulations demand the aircraft retains enough energy for a 30-minute flight reserve after completing the mission. If your 1% error happens to be on the low side, you could be dipping into that vital reserve without the pilot even knowing it.
How do you even achieve that? I mean, with the battery aging, a noisy generator, massive temperature swings, simple Coulomb counting, just tracking energy in and out, must be completely inadequate.
It is. It's a great baseline, but it suffers from drift. It can't account for efficiency changes or parasitic losses. The mandate requires advanced closed-loop estimators, specifically citing things like the extended Kalman filter, or EKF, or even neural network algorithms.
The Kalman filter.
The EKF is essentially a recursive, self-correcting algorithm. It takes the Coulomb count, it compares it with the measured voltage and temperature, and it uses a complex mathematical model of the cell to constantly refine and correct its own estimate. It's a feedback loop, continually reducing its own error based on real-time physics. This continuous self-correction is the only way to meet that sub-1% accuracy mandate across 1,600 cycles a year.
Okay, next up is SONH, state of health. This seems crucial, given that high utilization rate. The spec says you have to monitor specific internal characteristics, not just external symptoms. What are those?
The core health metrics are DC internal resistance and AC impedance. As a battery ages, its internal resistance goes up. This makes it harder to pull power out, and it generates more heat. The BMS needs to track this change rigorously to predict the remaining useful cycle life and, most importantly, the remaining usable energy capacity.
So the SOH model is dynamic.
Highly dynamic. As the internal resistance increases, the BMS has to automatically communicate a reduced available power envelope to the VCU. If the battery is too degraded, say, the resistance has spiked by 40%, the BMS enforces a lower SOP limit. It prevents the pilot from demanding the full power needed for takeoff, ensuring the aircraft always operates within its safety margin, even if that margin has shrunk due to aging.
And this brings us to the ultimate metric, the one with the most trauma. SOP, state of power. Why do you, as an architect, consider SOP the single most critical safety metric the BMS generates?
Because SOP is forward-looking. So C tells you how much fuel you have right now. SOP tells you how much thrust you can deliver in the next 2 minutes. And in aviation, the ability to deliver transient thrust when you need it is absolutely non-negotiable.
And the requirement is very specific.
It is. Real-time prediction of available peak power 30 seconds up to 2 minutes into the future. Why 120 seconds? Because we are preparing for the worst-case scenario, the balked landing or go-around maneuver.
Okay, let's inject some drama here. Paint this picture for us. What makes the balked landing the ultimate stress test for the BMS?
Imagine this. The aircraft has just completed a long mission. The battery is depleted, maybe down to 30% SAW. It's landed in a cold city, so the internal resistance is already high. The pilot is just minutes from touching down when the tower suddenly orders them to abort the landing unexpected traffic on the ground.
Oh, wow.
The pilot has to slam the collective, demanding maximum absolute peak power to transition from a controlled descent back into a high-rate climb and get away from the ground immediately. This is the moment when the battery is at its minimum energy and maximum internal resistance. If the SOP prediction is even slightly optimistic, the voltage will sag too low, the system will cut out, and the aircraft will lose thrust mid-climb.
Catastrophic.
The BMS must guarantee 120 seconds ahead of time that the energy needed for that crucial, violent power spike is absolutely available. If it fails here, the result is catastrophic loss of control.
That concept, that 10 to the -9 commitment, is what dictates the entire architecture. The sources make it so clear that the fundamental principle driving this whole spec is safety must take priority over function and performance. If there's a trade-off, safety wins every single time, which means you have to eliminate single-point failures.
That's exactly right. We can't just build a reliable system. We have to build a system that is provably safe even when things fail. The first step is assigning criticality. Because a battery failure leads directly to loss of thrust, the core protection logic monitoring, cell voltage, current, essential thermal functions, all of it has to be classified as Design Assurance Level A, DALA.
Okay, for listeners who aren't in aviation certification, what does classifying something as DLA practically mean for the engineers building it?
It means we enter a realm of extreme rigor. DLAA components require mandatory compliance with specific aviation standards. DO 178C for software and DO 254 for hardware. The resources, the cost, the time required for verification under these standards are just staggering.
And for software, DLA demands a 100% MCDC testing.
Modified condition decision coverage. This is perhaps the hardest requirement to meet. It means every single condition within every single decision statement in the flight critical code must be tested. You have to ensure it behaves as expected, even when combined with other conditions.
Can you give us an analogy for what that proves?
Sure. Imagine a complex logical statement. If temperature is high or voltage is low, AND, current is above threshold, then cut power. MCDC doesn't just check if the statement works when the temperature is high. It checks if it works when the temperature is high and the voltage is low. And then also when the temperature is high and the voltage is nominal, you are testing every single permutation to prove there are no hidden, obscure lines of code, no logical paths that could be accidentally triggered by some unforeseen combination of failures leading to an unexpected shutdown. It eliminates ambiguity down to the line of code level.
That is an incredible level of testing. Now, how does the architecture support that 10 to the -9 target? You can't just rely on one computer.
Absolutely not. Achieving that number mandates the elimination of all single-point failures, SPOFs. So the P13 system design requires a massive move toward a 4 times redundant architecture and a distributed power topology. For example, if you have 6 independent, physically separated battery packs feeding distributed motors, the loss of one pack or its BMU must not affect the other 5. The system has to automatically reconfigure to sustain flight.
But just having 4 identical copies can introduce a different kind of risk, which the source material calls out. You need heterogeneous redundancy. Why is that intentional dissimilarity so important?
It's the highest level of risk mitigation. If you use 4 identical microcontrollers from the same supplier running the same core software, you risk a common mode defect.
A single flaw that takes out all 4 at once.
Exactly. It could be a flaw in the chip design itself, a vulnerability in the specific compiler you used, or a bug in a standard library. If that one flaw exists, all 4 redundant channels could fail simultaneously, defeating the entire purpose of redundancy. So, heterogeneous redundancy mandates that the main MCU and its supervisory chip must come from different suppliers or use fundamentally different architectures. Say you combine a high-speed ARM core with a deterministic, simpler FPGA. This ensures that if a silicon bug takes down the ARM processor, the FPGA backup is immune to that particular defect. It's expensive, it's complicated, but it's the only way to prevent a common mode systemic failure.
I can see why it's necessary. Okay, finally, what is the ultimate non-negotiable safety barrier? We've covered software and hardware redundancy, but what happens if everything fails?
That is the hardware overvoltage protection mandate. This is the absolute red line. The BMU has to contain a hardwired, purely physical circuit, completely separate from the main software and processor. And this circuit constantly monitors for extreme overvoltage events. If that voltage exceeds a predefined physical limit, This circuit must have an independent path to trigger the main contactors to open, disconnecting the battery from the bus.
Bypassing everything.
Bypassing the VCU, the main MCU, any operating system. It is a fundamental, non-software dependent safety circuit. No programming error, no processor lockup, no network congestion can be allowed to override this final safety mechanism, because voltage runaway means instant failure.
The challenges we've discussed so far apply on the ground, but now we have to account for the physics of the aerospace environment. We're talking 800 to 1,000 volt systems operating at high altitudes, maybe up to 25,000 feet.
The altitude is the critical environmental factor here, and it introduces a dangerous physics problem governed by Paschen's law.
Paschen's law.
Most people assume air becomes a better insulator at high altitude because it's thinner. But Paschen's law shows us that air is weakest. Its dielectric strength is lowest at intermediate low pressures, exactly what you find between 15 and 30,000 feet. As the air thins, the mean free path for electrons increases, making them more likely to gain enough energy to cause an ionization cascade.
So on the ground, 800 volts might be perfectly contained, but when you fly up to 20,000 feet, the air between two conductors suddenly becomes conductive.
That is precisely the danger. So the specification mandates that the BMS packaging, the physical design of bus bars and connectors, must correct the required creepage and clearance distances, the physical gap between live parts. If those distances are insufficient at altitude, the high voltage will cause partial discharge, or corona. It's a localized electrical breakdown of the air. You can hear it as a hissing or sizzling noise.
And that's bad.
It is. It might not short the system immediately, but partial discharge slowly erodes the insulation barrier over time. This continuous degradation leads to carbonization, tracking, an inevitable catastrophic failure of the isolation layer. The BMS has to guarantee high voltage integrity under those low pressure conditions.
The rigorous architecture and redundancy, they're meaningless if the data foundation is flawed. That 10 to the negative 9 commitment rests entirely on the quality of the sensor inputs. So we need to look at the microspecs that differentiate an aviation-grade BMS from anything automotive.
Let's start with the most precise requirement: cell voltage accuracy. The mandate is clear and it is shockingly strict. The measurement error must be less than or equal to plus or minus 1 millivolt.
1 millivolt. Let's put that in perspective. Consumer-grade measurement devices often have an error range of 5 to 10 millivolts. Why does a difference of just a few millivolts matter so much?
It's entirely dependent on the cell chemistry. A lot of eVTOL developers are looking at lithium iron phosphate, LFP, because of its thermal stability and lifespan. The problem with LFP is its extremely flat voltage plateau across the middle 80% of its charge range.
Okay, so the voltage doesn't change much as it discharges.
Exactly. On this flat curve, a massive swing in state of charge might only correspond to a voltage change of 50 or 60 millivolts. If your sensor has an error of plus or minus 5 millivolts, that error is now a huge percentage of the total voltage swing. Your SAC estimate becomes wildly inaccurate. Millivolt precision is the only way to reliably estimate the SOF in these chemistries and prevent localized overcharge or discharge within individual cells.
So it's less of an engineering ideal and more of a physical necessity driven by the chemistry itself.
Precisely.
Okay, next, current accuracy. The requirement is less than 0.5% of the full-scale range. Again, why such an expensive, hyper-accurate current sensor?
Because of the massive dynamic range we're dealing with. We go from hundreds of amps at takeoff to just tens of amps at cruise and back up again. If you have a 1% error, it looks small on paper. But when you integrate that error over 1,600 cycles a year using Coulomb counting, the long-term accumulated error, the drift, it just destroys the reliability of your SOSH estimate. High precision is the guardrail against that cumulative drift.
And finally, thermal sensing. The spec calls for multi-point temperature sensing, going way beyond just module monitoring. What's the new standard?
The standard is moving toward at least one sensor per cell group, but the ideal is a distribution that covers the cell core, the surface, and crucially, the terminal and electrode connection points.
Why the terminal specifically?
Because that high C-rate discharge forces massive currents through the connecting tabs. Any minor fault in a weld or a connection point instantly becomes a high-resistance spot that generates intense, localized heat, a hotspot. Traditional, average module temperature monitoring would completely miss this. Multi-point monitoring builds a detailed thermal map that can detect these localized spikes, which are often the first, most reliable precursors to thermal runaway.
Moving from accuracy to timing, the data acquisition needs to be fast and perfectly synchronized. The minimum sampling frequency is over 1 kilohertz, once per millisecond. Why so fast?
We need that speed to capture the transient voltage behavior caused by the power electronics, specifically the silicon carbide or SiC inverters. SiC switching is incredibly fast and efficient, but it creates very high-frequency electrical noise and voltage ripples on the bus. If the BMS samples too slowly, it misses these transients and you get distorted data.
But the absolute mandate, the hidden bedrock of that SOP calculation, is synchronous sampling. It relies on a global clock. Why is this so important?
This is a critical point. The entire architecture is based on SOP predicting internal resistance. What happens if the data isn't perfectly synchronized?
The sources really highlighted this. If the cell voltage and the pack current are sampled asynchronously, even a millisecond apart, how does that corrupt the calculation of R equals dV over dI, the internal resistance?
It creates what we call phantom voltage. During a flight maneuver, the current, II, is spiking rapidly. If you measure the voltage, dV, at instant t1, but you measure the current, dI, at instant t2, just a hair later, you're now calculating resistance based on non-contemporaneous data. Since I is moving so fast, your calculated resistance is corrupted by computational error, not by actual physics.
So the math is wrong.
The math is fundamentally wrong, and that error completely destabilizes the internal resistance model. Since internal resistance is the key variable for predicting future SOP, asynchronous sampling destroys the reliability of the ultimate safety metric. Synchronous sampling, timestamped by that global clock, eliminates this instability.
Let's talk about thermal runaway, TR. It's the apex threat for any lithium battery system. The spec demands the BMS actively seeks out precursors long before a cell gets critically hot. What are these advanced early detection mechanisms?
We're moving beyond just temperature and voltage. The first precursor the BMS has to look for is pressure monitoring. Before a cell has a temperature spike, it often enters an initial venting phase. Gases are released. And this causes a slight but measurable change in the internal cell or module pressure. Detecting that pressure change can provide an invaluable lead time, 30 to 60 seconds of warning before the runaway really accelerates.
A full minute. That's a lifetime in an emergency.
Absolutely. It's critical time for the crew to initiate procedures or for the BMS to physically isolate that pack.
And what about electrical precursors?
The BMS has to continuously perform insulation impedance analysis. A nonlinear, sharp drop in insulation resistance within a cell or a module is a major red flag. This often signals the beginning of internal dendrite growth or microsorts that prenate the cell, leading directly to a full thermal event.
And the third mechanism uses that high-speed data we just talked about, voltage ripple analysis.
Yes. The high-frequency sampling lets the BMS look at the noise patterns on the bus. When a cell experiences internal physical degradation, microshorts, movement of electrodes, it creates unique acoustic and electrical noise signatures. The BMS algorithms can use high-frequency analysis to detect these patterns, revealing internal problems before they manifest as a voltage drop or a major temperature increase. It's essentially listening to the cell's physical deterioration.
That's a fascinating look at prevention. But even in a DALA system, we have to assume prevention can fail. What are the requirements for physical containment under EASA MOC3 and DO3OENA?
If a thermal event occurs, the battery structure and the BMS must cooperate to achieve two absolute mandates. First, non-propagation. The thermal energy from the failing cell cannot be allowed to propagate to adjacent cells. This often requires advanced, lightweight thermal barriers like aerogel insulation between cells. If the event spreads, the entire pack is lost, and that defeats the whole redundancy strategy.
Okay, and the second mandate?
Venting and containment. Thermal runaway produces extremely hot toxic gases and often flame. The BMS housing has to manage this safely. The gases and flame must be routed outside the aircraft cabin through dedicated exhaust valves. And critically, the battery housing itself must maintain structural integrity and show no visible flame penetration for at least 15 minutes. This ensures the aircraft has adequate time to execute a safe landing after the event starts.
So the BMS is the nerve center, connecting the high voltage side, the control side, and the cockpit. To maintain that DALA safety level, all communication and interfaces have to adhere to these rigorous aviation standards. Everything has to be perfectly deterministic.
That's right. When you're talking about the safety-critical connection between the BMS and the VCU, standard data protocols like consumer Ethernet are just insufficient. They're probabilistic. Data arrives most of the time, but the latency, the delay, can jitter unpredictably.
And unpredictable delay in power information is mission critical.
Precisely. If the VCU requests the SOP and the data is delayed by 50 milliseconds during a high-speed maneuver, the VCU is acting on old data. So the spec mandates deterministic protocols like T-Ethernet or AFDX. These are time-triggered systems that guarantee fixed, non-jittering latency. Data always arrives in the exact, guaranteed window.
What about inside the battery box? That high EMI environment, the communication between the main controller and its slave units.
For the internal bus, dual redundant systems are required, often using SAN-FD or differential buses like ISO-SPI or TPL. This is essential because the 800-volt size switching creates massive electromagnetic interference, EMI. These redundant differential buses are robust against that noise, ensuring the millivolt data captured by the slaves is accurately transmitted back to the main controller.
The sources also hint to the cutting edge, wireless BMS or WBMS. This seems like a massive potential gain, but what's the core challenge?
Oh, the benefit is huge. Up to a 30% weight reduction by getting rid of complex, heavy wire harnesses. And you simultaneously remove the biggest fire risk, the wiring itself. But the core challenge is passing DO-160G electromagnetic compatibility testing. In a severe EMI environment, proving that a wireless signal has 10 to the -9 reliability, that it will never fail to report a critical cell voltage, is an engineering mountain to climb. The signal integrity has to be guaranteed under all noise conditions.
Finally, let's talk about the physical safety mechanism on the connectors. The high voltage interlock loop, or HVL.
The HVIL is a fundamental physical safety feature. The auxiliary HVIL pins on high-voltage connectors are designed as last to connect, first to disconnect.
What does that mean?
It means if a maintenance engineer or failure causes the connector to start pulling apart, the HVIL circuit breaks first. This physically cuts off the current flow through a contactor before the main power pins physically separate. It prevents extremely dangerous high-voltage switching arcs that could cause fires or severely damage the terminals. It's a critical physical design principle.
Given the reliance on these incredibly complex algorithms, like the EKF, theoretical design and peer review are only the starting point.
The system has to be proven through the rigorous, step-by-step V-model verification process.
The initial phase is virtual integration, using model-in-the-loop and software-in-the-loop simulation. This is where we break the algorithms in a safe, controlled digital environment. We push the SOC algorithms to their absolute limits. We simulate a flight where the temperature drops to -40°C, while simultaneously modeling a virtual battery that has 30% capacity degradation. The algorithms must still converge, maintain that sub-1% SOG error, and accurately predict SOP under those worst-case combinations.
You're trying to find the one corner case where it fails.
We might run 10,000 simulated missions just to find that one case where the EKF drifts.
Once the virtual model is robust, you move to reality simulation, hardware in the loop, or HIL testing. This is the ultimate stress test for the actual physical BMS unit. HIL is where we introduce calculated sabotage. We connect the real BMS hardware to massive simulators that mimic the 800-volt bus, the motors, the generator, millions of permutations of cell behavior. Then, engineers intentionally inject specific hardware faults. A broken cell voltage sensor wire, a temperature sensor that starts reading 10 degrees too high, a communication node failure. The purpose is to verify that the BMS doesn't just register the fault, it has to correctly identify it, switch instantly to a redundant algorithm to maintain power estimation, and initiate the safest isolation procedure, all without a momentary disruption of stable power. If the system hiccups, it fails HIL.
And finally, integrating it all into the vehicle's power plant via Ironbird testing.
The Ironbird is the full power ground rig. It's a physical mock-up of the entire P13 electrical system. For the hybrid, a critical test is simulating that power handover when the ICE starts up and engages the P1 generator to recharge the battery. That generator startup creates massive electrical disturbances, intense transient voltage spikes. The BMS has to demonstrate its ability to filter, absorb, and suppress those spikes, maintaining a clean, stable DC bus voltage for the motors.
After all the simulation and testing, we get to the final acceptance criteria, the red lines. These are the non-negotiable proof points for type certification. They demonstrate that the 10 to the -9 commitment has been physically met.
The first and most important is survivability. This test proves the fail operational architecture. While the system is running at high power, an engineer physically disconnects or disables any single BMU or communication node. The requirement is that the entire energy storage system must automatically reconfigure, shed the failed component, and allow the remaining system to maintain a stable hover for a minimum of 10 minutes.
Enough time for an emergency landing.
Exactly. Second is thermal containment. This verifies the physical structure. A single cell is deliberately forced into thermal runaway, a violent destructive event. The battery package surface must show zero visible flame penetration for a full 15 minutes, and the toxic gases must be contained and routed outside the aircraft. They cannot vent into the cabin or cause secondary damage. It is a pass-fail test with zero tolerance.
And relating back to Paschen's law, what's the final check for high-altitude electrical safety?
That is the high-altitude electrical integrity test. In a vacuum chamber simulating 25,000 feet, we measure the partial discharge inception voltage, the PDIV, the moment corona begins. That PDIV must be engineered to be greater than 1.5 times the system's absolute peak operating voltage. We are proving, under reduced pressure, that the insulation margins are safe and the high-voltage isolation remains absolutely intact.
And finally, the long-term proof of the algorithms. Sending calibration accuracy.
This test validates the cumulative performance of the EKF and the SOH models. After the aircraft completes a full complex mission cycle, takeoff, cruise, go around, final approach, the actual physical state of charge is measured. That measured value is then compared against the BMS's final estimated SOS. The difference must be accurate to within 1% of the actual physical measurement. This proves the algorithms have successfully navigated all the variables: temperature, high sea rates, generator ripple, aging without drifting off course.
This has been an incredibly detailed deep dive into what is, arguably the most rigorous component of modern flight systems. When we look back at the nuggets we've uncovered, the story is so clear. The P-13 BMS is a radical departure. It's a leap from the automotive fail-safe mindset to the aviation fail operational mandate.
Absolutely. The need for DALA development means that every single decision, from the choice of semiconductor to the testing methodology, is driven by the fact that failure is not an option. We are dealing with an uncompromising 10 to the negative 9 reliability standard. We saw that in the staggering rigor of 100% MCDC testing and the engineering marvel of heterogeneous redundancy, designed specifically to avoid those common mode defects.
And let's not forget the sheer technical precision required. Plus or minus 1 millivolt accuracy, driven by the physical limitations of the cell chemistry itself, and the life-or-death nature of the SOP algorithm, which has to look 120 seconds into the future to guarantee the aircraft can handle the maximum stress of that balked landing maneuver right when the system is at its weakest. This is truly a flight-critical system rooted in an uncompromising aerospace philosophy.
And this leads us to the final fascinating challenge outlined in the specification, a provocative thought for you to consider. The path to maintaining that 10 to the negative 9 reliability over the fleet's lifetime requires the use of cloud digital twin technology. The BMS must not be an isolated component. It has to continuously feed data on those 1,600 annual cycles per aircraft into a centralized data platform.
A digital twin?
A digital twin of the entire fleet. This cloud platform synthesizes the operational data from every aircraft to constantly refine and optimize the degradation models and predictive maintenance algorithms. It suggests that the safety commitment doesn't end with type certification. Rather, the BMS integrates with the entire fleet's collective operational intelligence to ensure that the promise of 10 to the negative 9 reliability holds up across the operational lifespan, continuously learning and adapting as the physical batteries age in the real world.
The complexity of these hybrid systems and the sheer frequency of the flight profiles, it makes that kind of ongoing digital analysis mandatory, doesn't it? When physical energy density is your limiting factor, continuous fleet-wide data-driven optimization becomes the ultimate tool for maximizing both safety and commercial viability. Something to think about the next time you look up at the sky.